can start.
Yeah. So my name is Dipika Badri. I'm a second year master's student in electrical engineering.
Yeah, I'm Yifei Wang, and I'm my first year PhD student in electrical engineering. And our project topic is the machine learning approaches for singing voice separation.
Yeah, so singing voice separation is of great importance in signal processing because it is used in many other applications like automatic lyric recognition, music information retrieval, and singing identification. So the process of singing voice separation consists of a similar procedure for all the different methods we are going to present. So the first step is to apply a short time Fourier transform to transform the mixed signal into the phase as well as the magnitude. Then the magnitude is fed into the model, which can be either GAN, unit, or RCPA, different methods which we are going to present. And the output of the model is then inversely transformed using the mixture space. And the final signal is the output signal, which is then compared with the input mix signal to find the accuracy.
Yeah, and there are many classical approaches for the singing voice separation. And all of these are based on the following assumption, namely the vocal component is sparse and non-vocal part is with low rank. And this feature can be seen as in the figure 2, which is an example of the spectrogram magnitude of the vocal part and non-vocal part. And we can clearly see some repeated structure of the non-vocal part. So we can assume that it is with low rank. And based on these assumptions from observation, many methods are developed. For instance, some low rank based method or dictionary learning based method.
The neural network based approaches are new methods and they're alternatives to the traditional approaches. They use deep neural networks to find the features of this voice and the background music from the mixture and separate them using different methods. One of them is deep convolutional unit and other are GAN, recurrent neural networks. In our project, we'll be showing comparisons between the classical approach, which is RCP approach, and then the neural network based approaches. We have two, which are unit based as well as GAN based approaches.
Yeah, here I will briefly introduce the robust PCA method. So namely, here we denote M is the mixture magnitude. Here we want to penalize the nuclear norm of the L and the one norm of the S. Namely, we want to promote the low rankness of the L and the sparsity of S. And this robust PCA problem, it can be efficiently solved by an inexact augmented Lagrangian method. And after we solve this L and S from this robust PCA problem, we can apply a binary time-focusing masking trick to enhance the separation results. Namely, we construct a 0-1 binary masking based on these S and L, and we apply these masks to the mixture magnitude and to obtain these results. Then I will introduce a GAN-based method. So here we V and B and M, they denote the vocal part, background music, and the mixture respectively. And our goal is to infer the V and B from the M. The GAN model itself, it consists of generator and the discriminator, and they compete in a minimax game. Namely, the generator aims to generate fake samples based on the real data distribution, and the discriminator wants to distinguish the fake samples from the real data. To be specific, here we mainly consider the computational GAN. And the generator, it generates the vocal parts and background music from the mixture, and the discriminator, it takes in the mixture and the vocal part, and it tries to distinguish whether these vocal parts are real or fake. And the objective function for the conditional GAN is written in the following way, which is a minimax problem. And we train it with using the gradient descent and ascent. And here we consider two GAN models. One is the SDS GAN, which is designed for the task of the same voice separation. The other is the pixel-to-pixel GAN. It is based on a resonant generator and a pitch GAN discriminator. And they are originally from a task for image processing, and I adapted it for the signal processing.
Now I'll present the unit-based model. In the unit-based architecture, we have two different components. One is the encoder and one is the decoder. And And the encoder consists of 6 layers of striated deconvolution, whereas a decoder consists of 6 layers of deconvolutions. And we also use batch normalization and plain ReLU for encoders. For the decoders, we use leaky ReLU as well as batch normalization with dropout layers in the first 3 layers of decoder. The norm which we are trying to minimize is the L1 norm. The application, the output of this unit model is a mask which is applied to the input, which gives the output, and the loss minimized here is the mask applied to the input minus the output, which is the L1 norm of that. The same architecture is also tested with the L2 norm without the sigmoid activation function, which is present in the final layer with the L1 norm.
Okay, now we present some numerical results for our methods. So we apply SDFT with a window size of 1024 and a hop size of 256. The dataset is a public dataset MRI1K. It includes 1,000 sound clips lasting from 4 to 13 seconds with a sample rate of 16 kilohertz. And we evaluate the performance of separation, include the source to distortion rate, ratio, the source to interference ratio, and the source to artifacts ratio. These are classic metrics for evaluating the separation results. And these quantities are only evaluated on the vocal part. And we calculate the average weight average of these quantities over the data set. So here is some results from the robust PCA method. Namely, we mix the vocal part and non-vocal part with SNR in -5, 0, and 5. And with larger SNR, the vocal part is more louder. And we apply the binary masking trick with sigma equal to 1.5. And here, this is the result. We observe that it serves as a baseline of the singing voice separation. And we also know that a potential drawback of this robust PCA method is that it may misclassify the drum beats into the vocal part, because the drum beats, it is both sparse and low rank in the time frequency domain. And then we present some results from the GAN. Again, we randomly pick 250 audio clips for training and the rest for testing. And the training clips and testing clips are mixed with SNR equals to 0. And we also test with other training clips and test clips with different SNR with 5 and -5. And we further separate each audio clips into shorter pieces, such that the pieces after STFT, it is with shape 513 by 128. So from this table, we can observe that actually the GAN has very better performance than the robust PCA method, and achieves kind of 5 dB enhancement in both terms of the SDR, SAR, and SAR. And even on some dataset mixture rate that does not observe, for instance, SNR equal to 5 or -5. So this indicates that the GAN can learn the intrinsic mapping from the mixture to the clean voice. And on the other hand, we also observed that the pixel-to-pixel GAN is slightly not perform as well as the SDS GAN. And perhaps we may need to modify the GAN structure more carefully for the task of the audio processing.
Yeah, for the unit, we use 250 audio clips for the training and 125 for the testing. Each audio clip is segmented into 512 by 128 input after taking the SDFT, and they're clubbed into a batch size of 64. The results for the unit with L1 norm are seen to be poor. This could be explained due to the loss function wasn't decreasing as well as it should be, and it was not converging even after 500 epochs in initial trials. So there are various reasons for this could happen. First of all, the learning rate could have been tuned better. The hyperparameters for the optimizer as well as the weight initializations for the initial model weight initializations could have been done manually using bilinear filler or other weight initializations. The L2 norm shows better performance in SIR compared to L1 norm. That could be explained because the L2 norm averages over the various parts of the signal, and that can lead to a better inference but a worse distortion as it is seen in the data for the L2 norm. Now we'll present a few future work direction.
Yeah. For the robust PCA method, we may apply the binary masking trick to other methods to enhance the quality of the separation results. And for GAN-based methods, although these pre-trained GANs have reasonably good performance, we may train the GAN for more epochs and fine-tune the parameters to enhance the generalization ability on the test set.
For the unit-based method, the original paper which we have implemented on use the L1 norm, but there are a few other papers who use, for example, cross entropy loss and other kind of losses for training the model. So different kinds of losses could be tested to see which one fares better. Another thing which we could try to do is test the generalizability of unit as seen in GANs, because even unit is a very deep representation and it could be used to generalize the signals better.
Thanks you for watching.